Okay, algorithm efficiency. This is the part you really need to pay attention to for this chapter. This is what I really want you to take away from this. Okay, some algorithms are more efficient than others. Efficiency refers to how fast they run. Now, if something takes twice as long as something else, we're not real worried about that so much as we've got things like n squared. So does this take n times longer than something else? That's significant in big O notation. Okay, if we have a linear loop, that means we go through the loop once. So if we've got like a single for statement, we've got some code in here and it doesn't have any loops in it, then that is of efficiency n. So however big n is, it's going to happen one time. So we're going to go through this loop. The body of the loop will be executed n times. Okay, in this case, n is 1,000. Okay, application code is going to be executed 1,000 times, or n times. Now, if it were possible to cut this in half, it would be n over 2. But in big O notation, it doesn't really matter if we're multiplying by a half or multiplying by 2. It just wants a rough approximation. The controlling variable is multiplied or divided in every iteration. In a linear loop, the loop update either adds or subtracts. Okay, but here we're multiplying by 2, we're dividing by 2. And so it gets to the end, if we're multiplying by 2, it's going to get to the end faster than if we were just adding 1, right? So if we've got 2, 4, 8, 16, 32, etc., we're going to have fewer steps to get to 1,000 than if we were going 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, etc. The fact that that's faster, this is known as log n. And so log n is less than n. Okay, that's the main thing to remember about this. You don't have to understand what logs really are. Just understand that log of n is less than n. And so if you have big O notation of log n, that's faster than big O notation of n. If we have nested loops, then the number of iterations of the body is going to be the outer number of iterations times the inner number of iterations. So if you've got the inner going on I times and the outer going on j times, it's going to be I times j is the number of total iterations. If they were both n, you would have n times n, or n squared. Now, if we have one that is one that's log and one that's like this one, the j times equal 2, and we have one that's linear, it's going to be n times log n. Now, since log n is less than n, this is going to be less than n times n. It's going to be n times log n, okay, as they wrote down here, n log n. Quadratic means squared. So if you've got, this one's n because we're adding, this one's n because we're adding, so we have n times n, and that's going to be n squared. Now, if you have something that's dependent on the outer one, so while j is less than I, so it's not going to go all the way up to 10, it's going to just go up to whatever I is. So the very last time it'll go up to 10, but it's not, it'll be short, one short of 10, it'll really go through 9. So it's not going to be n squared, it'll be something less than that. So we'd end up with something like n times n plus 1 over 2. The largest term in that, though, is going to be n squared, as we'll see in a minute. Okay, big O notation. With the speed of computers today, we're not concerned with exact measurement of an algorithm's efficiency as much as we are with its general order of magnitude. If the analysis of two algorithms show that one executes 15 iterations while another's 25, they're both so fast we can't see the difference. Now, if one iterates 15 times and the other 1,500 times, yes, that's different. Okay, so if we have a nested loop, we would say the efficiency is n squared if both of them are linear. So we got n times n or n squared. We put a big O in front of it. And that's why it's called big O notation, is because we have a big O in front of it. Kind of simplistic thinking there, but it just got started. Somebody said it once and it caught on. If you have several things and you're trying to figure out what the big O notation is, you might have several things added together like we did up here, this one. If we multiply that out, that's n squared over 2 plus n over 2, okay? 1 over 2 is a coefficient there. You can throw away all the coefficients. That's the number in front of the thing. So if we've got like 3n squared plus 2n, you can throw away the 3 and the 2. And then you try to figure out which term is the biggest one for large n. Okay, so we have this. This is the thing you need to memorize right here. Log n, and then n. This is the fastest. Okay, log n, and then n, and then n log n, then n squared, n cubed, n raised to whatever. We call it n to the k. And then 2 raised to the k. That's a lot less efficient than, it's a bigger number of iterations, which means it's less efficient. And then n factorial is like 5 times 4 times 3 times 2 times 1, that's 5 factorial. N factorial is the biggest of all of them. For something like 5, it doesn't seem that big, but if you start putting something like 100 factorial in your calculator, it'll blow up the calculator. So it gets big in a hurry. Now, if we've got something like this, it's a half times n squared plus a half times n. Okay, we throw away the coefficients because in today's computers, it's just faster. And we're trying to get an overall idea, kind of the worst case scenario. And then we've got n squared plus n. Okay, which of those is the biggest? N squared. So this is called O. It's called big O of n squared. Okay, even though it's got this half and all this other stuff, it boils down to big O of n squared. That's what I want you to be able to do by the end of this chapter, is be able to tell me what the big O of any of these is. Okay, so we've got something like this, some coefficient times n to the k plus all this. The biggest one, we throw away all the coefficients, and then we've got this. The biggest of all these is going to be the n to the k term. And so this is big O of n to the k. Now, we didn't have any 2 to the n type terms, which might have been bigger. We didn't have any factorial terms. If we did, then it would be that one. Here is a chart that's got them in order from a number of iterations, smallest here to largest there, which means this one's the most efficient, this is the least efficient. This is some approximate number of iterations on a given type of algorithm. If you've got something that's c to the n and n factorial, if n is really big, your computer is probably not going to finish it in a reasonable amount of time. That's what it means, intractable. Okay, here's some charts on the different ones. If n is large, now if n is 1, that's here. N is 2, n is 3, etc. So log n starts at n1. There is no log of 0, so it doesn't start there. Log of 1 is 0, so it starts here. And then that's what this graph looks like as n gets bigger. And then n is this one. So if you've got like this number out here, actually this isn't 1, 2, 3. It's just kind of doing this in a generic way. But n is going to get bigger at a 45-degree angle. Okay. And then the next one was n log n, so that's here. Then we've got n squared. And so if you get one that's like here, you come way out here, you have to go way up, way off the screen to get to these. But they do keep going over. It doesn't like go straight up. It does keep slanting some. Here's an example. If we're going to add square matrices, If you don't know your math, don't panic. All that means is a matrix is a two-dimensional array. Let's say we've got two 3x3 arrays and we want to add them together. What that means is you take this element and you add it to that element and you put it there. You take that element, add it to that element, and you put it there. Take that element, add it to that element, and you put it there. Okay? It's 0 plus 3 is 3. Negative 3 plus 2 is negative 1. 4 plus negative 1 is 3, and so forth. Okay? That's not hard, right? Even if you haven't had the math. Okay, so to do that in a computer, you would loop until not the end, while not the end of the row. Then you would loop while not the end of the column, and then you process a row. So you're going to add matrix 1 and matrix 2 cells and store the sum in matrix 3. Okay? So this one's going to go through n times, and that one's going to go through n times. So it's going to be n times n, or n squared. Now, if you do have any of these math things to do, it will be well defined, so you don't have to already have had linear algebra to be able to do these things.